As you might guess, equations related to quadratic surfaces have quadratic terms. In this case, we're going to sketch and identify 4x squared plus 9y squared plus 9z squared is equal to 36. We're going to do it by considering traces in the three coordinate planes. So the trace in the xy plane, the trace in the yz plane, and the trace in the xz plane. We're going to do these separately though. In the xy plane, we know that z is equal to 0. So we have the equation 4x squared plus 9y squared is equal to 36, or x squared over 9 plus y squared over 4 is equal to 1. That is an ellipse with a horizontally oriented major axis. And I decided I would use good form and give you a grid here. And there's our trace in the xy plane. For our trace in the yz plane, we have that x is equal to 0, and we have the equation 9y squared plus 9z squared is equal to 36, or y squared plus z squared is equal to 4. As we know, that's of course a circle of radius 2, and again, this is the yz plane. And for the trace in the xz plane, we have y is equal to 0, and if y is equal to 0, then we have 4x squared plus 9z squared is equal to 36. We're back to an ellipse. X squared over 9 plus z squared over 4 is equal to 1. Now, how do we combine these into one shape in R3? Well, first things first, let's get ourselves a set of axes. Now, I don't have the luxury of this nice grid down here, but I can make do. What we see is that our shape extends to a maximum of 3 units on the x-axis. And so I'd like to represent 3 units out on the x-axis. And it does so in the positive and negative direction. And in order to help my eye believe that this is, in the perspective that it's in, I've tried to make these little hash marks parallel to the y-axis. So I'll put little marks, 3 and -3 there. And then we see that we extend as far as 2 on the y-axis. And so I'm trying to use roughly the same scale so that my eye will believe this. And then -2 there for the y, and then 2 for the y-axis there. And then our shape extends from z equals -2 to z equals 2. So I'm going to make a couple of tick marks on the z-axis. And I don't usually draw the negative z-axis, but I am in this case because we're going to have this shape that we're dealing with. Okay, now in the xy plane, I have this ellipse. So I'm imagining this kind of this football shape, this ellipse, in the xy plane. Let's see what we can do about that. And I think that's going to be okay. I could have used the tools that the iPad gives me, but here I wanted to kind of give you an authentic, this is how this might look. But I will use the tools of color. Now in the YZ plane, we should be looking at a circle of radius 2. So let me give that a shot and wish us all luck here. All right, I think I've done better before, but I'm, again, going to give you an authentic view of what this is. And then in the XZ plane, we're looking at, again, an ellipse. And we can kind of see how that shape is going to look here. And then down here. Now, this looks like a bunch of just, it looks like planetary orbits to me. Or it looks like exactly what it is, a series of kind of elliptical objects that aren't making one shape. And so again, to help the eye believe what we're looking at, I'm going to give it lines of contour, and then I'll do them in multiple directions here. And now we can kind of see what this is. I wasn't sure I really believed that, and so I drew more lines of contour. This is something called an ellipsoid. It's actually what footballs are made of. Well, it's not what they're made of, but this is the same shape as a football. And you can basically imagine that it's this ellipse over here in blue, and somebody spun it around the x-axis, right? That's kind of what I see here. Now, if we didn't know what we were going for, how would we know what that was? Well, that's a good question. So let me show you what we're going for. Here I have a series of images from the textbook. And what we just looked at was an equation that was of the form x squared over a squared plus y squared over b squared plus z squared over c squared is equal to 1. Traces are ellipses, and that's the ellipsoid. What you're looking for is basically which one of these forms does the equation that you're looking at match. Here we see an equation of a cone, and its characteristic is that it's got z squared on one side and x squared plus y squared on the other side. We have the idea of an elliptic paraboloid where we have z on one side and x squared plus y squared on the other side. Notice z is not squared. The hyperboloids are kind of tougher. They resemble the equation of a hyperbola in that we don't have all of the x squared, y squared, and z squared having the same sign, right? If two of them are positive and one is negative and the constant on the other side is 1, what we have is a hyperboloid of one sheet. And this is actually the shape that you see nuclear power plant cooling towers made out of, right? You may have seen shapes that look like this, and they are a hyperboloid of one sheet. Down here we see that if we have two of the terms that have negatives in front of them, and the third quadratic term is a positive term with a positive constant on the right hand side, then we have a hyperboloid of two sheets, and this actually most resembles the hyperbolas that we saw in previous courses. The hyperbolic paraboloid, we have x squared minus y squared equals z. And this is probably the toughest of all of them to draw. So I'd recommend if you're trying to draw one of these, have one in front of you. And really, if you start with the hyperbola on the edges and then kind of the saddle portion there, then you trace out the sides there, then that's a way to kind of convince yourself of what you're looking at. And then, of course, the contour lines help. So keep all that in mind as you're trying to graph these. And I don't have everybody memorize all of these. What I would say is I want you to be able to produce an ellipsoid, an elliptic paraboloid, and a cone. And in order to know what kind of cone you have or what the elliptic paraboloid is, then you're going to consider traces in the coordinate planes, but also traces for various values of, let's say, z. So let's consider a cone. Let's say we have a basic equation, x squared plus y squared is equal to z squared. What we want to do is consider the traces for various values of z. So we can let z equal 0, 1, 2, and let's say 3. For good measure, we'll say -3 as well. If z equals 0, then we have x squared plus y squared is equal to 0. That's simply the origin. If z equals 1, we have x squared plus y squared is equal to 1. That's, of course, the unit circle. If z equals 2, then we have x squared plus y squared is equal to 4. That's a circle of radius 2. And then moving on, we can see that for z equals 3, that our circle has a radius of 3. Likewise, if z is -3, our circle has a radius of 3. We can put these together and draw traces for various z values. For z equals 0, we have the origin. For z equals 1, we have a circle of radius 1. And what we're going to end up with is a series of concentric circles that are, to the best of my ability, equally spaced out. In the case of a paraboloid, an elliptic paraboloid, what you end up with is the circles are closer and tighter together near the origin, and then as you get higher and higher, the circles get bigger and bigger. And so as you move out from the origin, the circles for regular increments of z values get spaced farther and farther apart. Well, in the case of what we've just drawn, what we would have is a cone, and it's identified here as horizontal traces being ellipses, but in the case of what I just drew, the horizontal traces would be circles, and so it would be a circular cone.